Welcome back to the Packet Lab. Today's lesson is going to be a continuation in the frame relay series, and in this lesson we're going to take a look at frame relay topologies and designs. So if you viewed the first lesson, the Introductions and Concepts frame relay lesson, you will have learned that the frame relay protocol does have some advantages over point-to-point leased lines, and we'll get into more detail about what those advantages are and how they are quote-unquote actualized, don't you love that word, in the next slide. But what this lesson is going to be about is just showing different types of designs, basically topologies more than methodologies, and which of those designs really takes advantages of these frame relay benefits. So one of the biggest selling points for frame relay over point-to-point WAN connections, sometimes just referred to as leased lines, although I don't like that term because I think that any type of line that you're paying a monthly fee for is a leased line, but that's semantics and we won't get into that. One of the big benefits is that you can have a number of frame relay virtual circuits or VCs on the same physical connection. So if you think about your router, you have a serial interface, and connected to that serial interface you have a T1 line. Now if you're using point-to-point connections, you'll only be able to use one point-to-point connection. It'll use that T1. Whereas with frame relay, you can have multiple virtual circuits that use that single connection to the frame relay cloud. So you could have 3 virtual circuits. You got T1 that's going to give you 24 64K channels, so you could split that 3 ways. Hell, you could go crazy and split it 24 ways. Each one's going to be a 64K virtual circuit. I wouldn't recommend that. You can even oversubscribe it, and we'll get into that a little bit later in these lessons, but you could actually have 24 128K circuits. Now I wouldn't recommend that because if they're all running at full speed, you're going to overwhelm your physical media. But the point here is that you're saving money in this case because you're only paying for one connection, and we're going to refer to that as the access circuit going forward from your router to the cloud. So there's a couple advantages to this. One, you only have one physical connection, so you've got that single T1 going to the frame relay cloud, and you could have multiple circuits on that. That also comes up as a benefit because you're not going to have to purchase separate point-to-point connections. So for each point-to-point connection that you want to make, you're going to have to purchase it from the service provider, and you're also going to have to provide an interface for that to terminate on your router. So if you have 3 point-to-point circuits, you're going to need 3, in this case, serial interfaces, whereas you could have a frame relay connection that has a single connection to the cloud, only using one interface, one physical connection, and have 3 virtual circuits on it. See where you can see where this not only makes management of your device easier, but it also saves you money. It's used to save you a whole lot more money because back in the old days, Cisco 2500s, they sold different models based on what interfaces were in those devices. I don't have the device numbers memorized, but like say a 2505 would come with one serial interface, one Ethernet interface. So if you need to add a second point-to-point connection, you'd have to get a different router because you couldn't upgrade those routers. So you'd have to buy a 2506. I'm just making up these numbers, so please don't email me telling me that I'm full of shit on the numbers. I know that so at that point you would buy, the 2506, let's say, and it had 2 serial interfaces and 1 Ethernet interface. When Cisco rolled out the 2600s, they introduced the concept of modular routers. The router would come with a couple of ports that were built into the device, but it would also come with slots. So you'd buy a router and there'd be empty slots, and they used to have stickers on the routers that said, fill these slots with functionality. So you'd buy cards. So you might buy a card that has a single serial interface on it, or you might buy one that has 2 serial interfaces on it, or you might buy one that has a couple of fast Ethernet. Basically, you could design that router to better fit your needs based on which cards you ordered. And you're really only limited by the amount of slots and the processing ability of the router itself. But I digress. My point being that it's still a cost savings, but it was a much bigger cost savings back in the day because whenever you upgraded or you wanted to add more connections, you would have to buy a new physical router rather than just a card. Anywho, I've beaten that to death, so let's go to the second point here. The second point is that frame relay hub and spoke design, which we'll look at in depth later on, allows for full connectivity to all endpoints through a single physical connection to the frame relay cloud. Now that's talking about a single physical connection at each endpoint. And we'll go over the hub and spoke design in more depth, and we'll get to the full mesh in just a bit here. But with the design, you can shave the number of physical connections just about in half compared to a full mesh point-to-point topology. So the 2 ways that you're saving money are basically on the number of circuits that you need to lease and on the amount of equipment that you need to provide for those circuits. Let's take a look at the different designs, and this is going to be a review for a lot of you. Full mesh. In a full mesh design, each endpoint is capable of reaching every other endpoint directly through a point-to-point physical or logical circuit. The number of connections needed for a full mesh is calculated with the following equation. You're probably aware of this equation if you've done any network studies. It's n times n minus 1 divided by 2, where n is equal to the number of endpoints. So if you have a simple network that has 3 endpoints, just imagine 3 routers, you're going to need 3 connections, and we'll see this in the next slide. It's not that hard to visualize. Each router connects to its neighbor. Unfortunately, as you grow your network, it becomes harder and harder to scale a full mesh because the required number of connections becomes a financial and management nightmare. So let's take a look at what I would consider a small network, 10 endpoints. At that point, you need 45 circuits, 45 connections. And not only that, but you can also, from this equation, determine how many termination points, provided that you're using point-to-point circuits. N minus 1 is equal to the number of interfaces that you would need to have on each router. So in your 10 router network, not only would you need 45 point-to-point connections, you'd have to have 9 serial interfaces on each device in order to pull this off. So you could see this doesn't scale well at all. So the pros for a full mesh, well, the big one is full redundancy. You're going to have a distinct connection to each router, and this probably gets a little easier to visualize when I have a visual for you, which will be in the next slide. The cons are it's expensive. Your circuit cost, if you're providing 45 circuits for a 10 router network, that gets to be very expensive. Router cost, you have to have routers that are able to terminate each of those connections. It's difficult to design, it's very difficult to manage, and it can result in complicated routing and IP addressing schemes. So it's really for those situations where you absolutely need full redundancy. There aren't that many full mesh networks out there. I remember at one point when I started studying it, they used to tell us that the Department of Defense had a number of full mesh networks. Even after just a minimal number of endpoints, it just gets to be too damn much. I can't imagine, 1,000 routers with full mesh. I don't even think that's possible because you have to have 999 interfaces on each router. So anywho, it's more of a theoretical, and you will use full mesh for your important parts of your network. Again, nobody designs a network and just says from the beginning, we're going to do full mesh for everything. We're going to do partial mesh. We're going to do hub and spoke. Almost all network designs are a combo platter when it comes to this. Okay, here we see a couple of full mesh designs, and the full mesh with 3 endpoints, like I said, there it is. That's pretty logical. Not a lot to it. At this point, it's very manageable. Here's just 5 endpoints, and you can see we have 10 circuits, and then each device is going to have the n-1, which is 4 in this case, connections. This might even be doable, but you can see that once you start scaling higher and higher, it just becomes, if not impossible, very impractical. Now, we've been showing point-to-point connections for these designs. Full mesh is possible with frame relay, and you would have one benefit in that you could have a single physical connection. Here's a full mesh with frame relay. So each router has an access circuit connecting to the frame relay cloud, and each of these dotted lines is a virtual circuit. So with 5 routers, it's not that big a deal. Each physical interface would have 4 virtual circuits on it. The problem is that when you start scaling this up again, once you get to 10, you could probably pull it off with a single physical interface as long as that's like a T3 or something like that. But you're going to have more speed on this end going to the cloud if you're going to keep packing those virtual circuits in there. Because even though you use a single physical connection, you always have to be aware of how much bandwidth is available. The higher the bandwidth requirements, the bigger that physical access circuit's going to have to be. Anyways, I just want to show this because it is possible to do this. You don't see a lot of full mesh with frame relay. It could be a benefit in that you could minimize the number of physical connections to the frame relay provider and still utilize a full mesh. I guess I should point this out since I do have it in the slide. While the benefit of a full mesh frame relay design would be that you could minimize the number of physical access circuits, you do run into the point where, and we'll revisit this later with the hub and spoke design, you would have a single point of failure. R1, if this was point to points, would have a connection R2, R3, R4, R5. It would have 4 connections here. Here it only has 1 and then 4 virtual circuits. But if something happens to this access circuit, suddenly R1 is down completely. So you have a single point of failure, and that would be the physical access circuit at each location. Next up is the partial mesh, and in reality, almost all of your designs are going to be partial mesh. If you want to get into logic with this, anything that is not a full mesh design is technically a partial mesh, because what a partial mesh is It's just any design that doesn't have full connectivity between each endpoint, from each endpoint to each other endpoint. So you could make a partial mesh by taking a full mesh and just removing one single circuit. The pros of the partial mesh are going to be that it's less complex than the full mesh, and it's also less expensive. The cons are that it's not going to be fully fault tolerant. So basically everybody would love to have the fully fault tolerant capabilities of a full mesh network, but the partial mesh is basically what you're going to end up with. So you're going to pick and choose which endpoints you want to provide fault tolerance to and how much of that fault tolerance you need. Like I said, logically, anything but a full mesh is a partial mesh. So even though you have designs like ring design, a bus design, star design, those are all really just part of a larger group, which are partial mesh. So we've taken the same 5-node network, and rather than making a full mesh, we make it a partial mesh. So in this case, we've let R1 retain connections to everybody. So it's got 4 connections. It's the n-1. But the rest of them, we just say, okay, well, you know what? I want to have a connection back to R1. Let's say this is our corporate headquarters or data center. And then I'll have a connection from each of these. So it's a combination of a hub and spoke with a ring, basically. So you get some fault tolerance. It's not full fault tolerance that you're afforded with a full mesh design, but you can also design it where it does not have single points of failure. And that brings us to the hub and spoke topology. And that's a design that many frame relay networks are going to use, because this design takes advantage of frame relay's ability to provision multiple virtual circuits on a single physical access connection, the access circuit. I'm going to actually peep this guy first before we discuss it so that you have a better idea of what we're looking at here. So this would be an example of a hub and spoke network, and again we're using our same 5 routers that we had before. So each of them have a single physical connection into the frame relay cloud. But what's going on here is they each have a virtual circuit, and R1 is going to be the hub in this case. So each of these guys is going to be a spoke, and the name probably, I didn't research this, but probably comes from like the concept of a wagon wheel. If you think of a wagon wheel, in the middle is the hub, and then each spoke goes out, and imagine an endpoint at the end of that. If you're all familiar with the star topography, that's basically what this is. Well, that's exactly what this is. It just doesn't look exactly like it here. So anyways, this is your hub, and in a lot of cases this is going to be your data center, your headquarters, your regional headquarters, whatever. These sites are going to be referred to generally as either spokes or remote sites. They have a single physical connection, and they all have a connection back to the spoke. The benefit is that you're paying less. You don't have the redundancy. You don't have point-to-point connection. So you have one connection, one access circuit, and then you also are only paying for a single virtual circuit. You're saying just send everything to the hub. So what you're saying here is that if I need R2 to talk to R4, I don't want a dedicated circuit there, because there's not going to be that much traffic from between these remote offices. Everything's got to go back to my data center. So the trade-off with this design is any spoke-to-spoke communications have to go through the hub. So if R2 is going to communicate with R4, it's not going to communicate directly. It's going to go up to R1 and then back out to R4. And the same way with the reverse traffic. It's going to go up to R1 and back to R2. And you can see that would happen with all of these. And we'll discuss that in a little more detail in just a bit here. I just wanted you guys to see what a hub and spoke network was before I start going through the pros and cons. And the pros of the hub and spoke design are that it's more economical. You can have less physical connections, less interfaces used on your routers, and also, in this case, less virtual circuits. Because we think back to that hub and spoke full mesh. Of course, we only had the single access circuit connecting to the frame relay cloud, but then we also had individual virtual circuits going to each of the endpoints. In this case, the spokes are only going to have a single virtual circuit connection back to the hub, just like we saw in that example. So you're cutting down on the number of virtual circuits as well as physical circuits. It's easy to manage. It's easy to scale. This is one of the big advantages is, whenever you want to add another site, it just becomes a spoke on the hub and spoke design. And that's pretty easy to scale. It's going to generally help you conserve layer 3 addressing. That's not such a big deal, so I'm not going to dwell on that one. One of the benefits of frame relays allows you to provide slower access speeds at the spokes and at the hub. So let's pop back over to that example real quick. Okay, again, R1 is our hub. Let's just consider this our headquarters, and these are all remote sites. So for the remote sites, say that they don't spit out a lot of data. Say that they're fine with 128K. So you can provision this virtual circuit to only be 128K. And each of these, could be 128K. Hell, you can make this guy, 512K, this guy 64K. You can have different speeds based on the data needs of your spoke. Whereas at the hub, you can have a full T1. So you can have partial T1s here and then a full T1 here, or a full T3, DS3, whatever you want to refer to it